My name is Tommaso Zugno. I'm a research engineer at the Huawei Munich Research Center, and today I will give you an overview of the TIMES project, where I'm involved as a work package leader. So this is a general overview of the project, as all the other projects that presented during this workshop is funded through the SNSJU funding framework. It's a Stream B project on wireless communication and signal processing. The project started on January 2023. So it's 1 year that the project has been active, and it will end on December 2025. The consortium is quite broad. It includes some universities such as Technical University of Braunschweig, University of Stuttgart, CNRS from France, and CNIT from Italy, 2 research institutes, Fraunhofer from Germany, and BIREX, which is an innovation center in Italy. A couple of industrial companies. We have Huawei, the Norwegian operator Telenor, and an industrial company from Italy called Etna, which is producing some packaging machines. And we have also an SME from Spain, that is Anteral, which is specialized on the design and fabrication of antennas and metasurfaces. The project is coordinated by CNIT, specifically by Professor Luca Sanguinetti from the University of Pisa, and the technical manager is Professor Thomas Körner from the University of Braunschweig. The vision of the project is to build a smart radio ecosystem that is working in complex scenarios and is able to offer similar performance as wired networks. And to achieve such goal, it builds upon 3 technological pillars. The first one is to exploit wide bandwidth and sensing-friendly capabilities of terahertz communications. The second one is to deploy intelligent terahertz mesh networks in smart propagation environments. And the third one is to enable high-definition integrated sensing and communications at terahertz frequencies. So the project is focusing on industrial scenarios, but in principle, all the solutions that will be developed throughout the project are applicable also to other verticals such as healthcare or automotive. These are the key objectives of the project. So we have the definition of use cases and requirements for future industrial applications, the derivation of new channel models for industrial scenarios that are based on real measurements, the design of novel solutions at the physical and MAC layers to enable highly efficient and reliable terahertz communications, the realization of front-end antennas and IRS is able to operate at terahertz frequencies, the design of a multi-goal and mesh-based radio access network is composed of active and passive nodes, where the terms passive here refers to intelligent reflecting surfaces, and the design of integrated sensing and communication functionalities and waveforms. And then at the end, some of the solutions together with our custom hardware components will be integrated in a proof of concept, and we will carry out some demonstration in real industrial environments. This is a list of the main innovations that the project is expected to bring. For example, we are studying novel physical layer solutions based on line-of-sight MIMO, fast beamforming, and electromagnetic signal processing for terahertz communications. We are studying a novel mesh-based radio access network architecture composed of active nodes and intelligent reflecting surfaces. We aim to achieve the so-called see around the corner functionality, which basically means to enable sensing in non-line-of-sight conditions with intelligent reflecting surfaces. And also we have the proof of concept, as I said. This is how the project is structured. We have 5 technical work packages. Work package 2 about the identification of scenarios, requirements, and KPIs. Work package 3, where we are collecting some channel measurements and developing channel models for terahertz frequencies. In work package 4, we are working on the concept of intelligent terahertz mesh networks assisted by integrated sensing and communications and intelligent reflecting surfaces, and developing some solutions at the physical and MAC layers. And the work package 5, which is working on the development of our hardware components, including front ends, antennas, and IRSs. And then work package 6, which will take care of the integration and the realization of the proof of concept. In the next few slides, I will give you an overview of the work that we have done so far in the context of these different work packages. Let's start with Work Package 2, where we basically studied scenarios, requirements, and KPIs for our project. We identified 15 different use cases that are spanning six different application areas, all related to industrial scenarios. For example, we have predictive maintenance, mobile robot management, flexible and modular factories, highly dynamic control, AR, VR, and digital twins, and seamless field bus substitutions. So we analyzed these use cases in detail, and we derived the requirements both in terms of communications and also in terms of sensing. Here you can see a representation of the requirements, but you can find more detail in our deliverables. In Work Package 3, we are working on channel measurements, and we considered three different industrial scenarios. We are considering a small industrial workshop, a big industrial workplace, and a robotic laboratory. So in the small workshop, we collected some channel measurements by emulating wireless links between different industrial machines and also within the same machine, putting the receiver and the transmitter inside the same machine. And also we did some measurements by emulating, let's say, radar configuration, where both the transmitter and the receiver are collecting measurements for sensing purposes. Then we have the measurements that we took in the big industrial workspace, where we used some directional configurations. And here we evaluated the impact of aligned and mismatched configurations. So when the transmitter and the receiver antennas are completely aligned and when there is some mismatch. Instead, in the robotic lab, we emulated a wireless link between different robotic arms, and we evaluated the impact that static and moving blockers have when they obstruct the line of sight path between the two arms. Here there are some results. So we started with the characterization of Pathloss and large-scale parameters in line of sight and non-line of sight conditions. So we selected multiple positions for the transmitter and the receiver. And for each position, we collected measurements in three different frequency bands. So we consider sub-6 GHz, millimeter waves, and terahertz bands. And we are now analyzing these measurements, and our goal is to understand the different propagation conditions that are experienced in these bands. In the same scenarios, we also emulated this radar setup where we performed some measurements with sensing purposes. For example, in this experiment, we were trying to detect a forklift that was moving in the scenario by using the impulse response from the channel. These are the results. So we have one of the results that we collected in the robotic lab. Here, as I said, we emulated a wireless link between two robotics arms, and we were trying to understand the impact of blocking obstacles. And we did similar measurements in the small industrial workshop, but in this case, we consider a slightly different configurations. Basically, we put the transmitter in front of a machine and the receiver inside the machine. In this case, was a CNC machine. And we were opening and closing this protective window in front of the machine and evaluating the impact on the terahertz link. And as you can see here, there's a clear drop in the received power, and this is due to the metal frame that at a certain point is obstructing the terahertz link. Let's move to Work Package 4, which is about intelligent terahertz mesh networks assisted by integrated sensing and communications and intelligent reflecting surfaces. Here we are studying four different topics, and the first one is about physical layer enhancements for terahertz links. We are considering two different tracks, let's say. So the first track is about how to exploit the near-field propagation conditions that are experienced at terahertz frequencies to improve the communication performance. As you may know, at these frequencies, the typical communication ranges in indoor environments, such as factory environments, are entirely in the near-field region. And we are trying to exploit this fact by using some physical layer solutions based on line-of-sight MIMO. In our latest deliverable, we carried out a performance analysis to understand the performance limits of this technology when operating at terahertz frequencies. And here you can see some results where we studied the impact of the bandwidth and array size and the transmit power. The second track is about the measurements, modeling, and mitigation of radio frequency impairments. Here we are considering the front-end architecture that will be used for the fabrication of our own terahertz transceivers. And we are basically isolating the effect of each component in the radio frequency chain to understand if they have nonlinear behaviors. And we are building some models able to model these non-idealities. Then we are also exploiting these models to build physical layer schemes that are able to mitigate their effect on the communication link. For example, one of the schemes that we proposed in our latest deliverable was based on typical physical layer solutions such as carrier aggregation and adaptive OFDM numerology to mitigate the impact of time frequency synchronization errors on terahertz OFDM transceivers. The second topic related to work package 4 is about the integration of sensing and communication functionalities. Here we are studying a new waveform that is based on DFT spread of TM, able to achieve high performance both in the communication and sensing domains. Here you can see one of the preliminary results that we have where we compare the sensing performance of our proposed solutions together with OFDM and DFT spread FDM. And as you can see, OFDM is able to achieve the best sensing accuracy, but it pays in terms of peak to average power ratio, which is something that we want to minimize at terahertz frequencies. And while our proposed solution is able to achieve a good trade-off between the sensing accuracy and peak to average power ratio. A second aspect that we're studying related to this topic is how to exploit these sensing functionalities to assist terahertz communications. In particular, we developed an algorithm for the tracking of extended object. And this algorithm can be used, for example, to detect objects in the surrounding of our terahertz links and use this information to predict possible link disruptions. The third topic is about terahertz communication and sensing in smart propagation environments. And here we are trying to exploit the usage of intelligent reflecting surfaces, both for communication and sensing purposes. We introduced the concept of frequency selective IRS or metaprism, as you want to call it, which is basically a surface that is able to reflect different subbands of the incoming signal towards different directions. And we are exploiting this concept to improve the coverage and also to enable sensing in non-line of sight conditions. Other aspects that we are studying in this regard are related to channel estimation for IRS-aided links, and also the characterization and mitigation of radio frequency impairments for IRS links. In this case, we are, for example, evaluating the impact of phase errors in the IRS elements to derive the optimal bin design. The last topic related to work package 4 is about the design and optimization of intelligent and multi-goal mesh networks. Here the goal is to develop an intelligent network controller that is able to manage a dynamic environment with multiple nodes having different constraints, both in terms of communication and sensing. Here we are developing a MAC layer scheme that is able to adapt to the different constraints of the nodes and satisfy them simultaneously. The second aspect that we are working on is about the distributed and cooperative blockage predictions, where we are exploiting the information available in nearby nodes to predict the possible blockage events. Instead, regarding work package 5, so in this work package, we are developing our own hardware components. In particular, we are designing and fabricating our terahertz front ends that will be able to operate at 300 gigahertz. We are realizing our own terahertz antennas. We are using two different solutions, one based on slotted waveguide and the other one based on phase delay line. And then we are also designing and realizing, and we will realize our intelligent reflecting surfaces. We are considering two different solutions. One which is based on multiple static metasurfaces. So the idea would be to build a mosaic of multiple static metasurfaces with on-off capabilities, illuminate this mosaic and turn on and off the single elements of this mosaic depending on the overall behavior that we want to achieve. And the second solution is based on liquid crystals that are put on top of the surface to achieve the reconfigurability. In Work Package 6, we will integrate part of the solution developed in Work Package 4 and the hardware components developed in Work Package 5 to build our proof of concept. And we will use this proof of concept to carry out two different demonstrations, one with high gain antennas and static surfaces, and another one with steerable antennas and configurable surfaces. We will perform these demonstrations to different industrial premises. One is the BIREX pilot line, which is an example of digital factory where BIREX is testing new solutions for industrial manufacturing. And the other one is the AETNA Tech Lab, which is the most advanced laboratory in the packaging field, where AETNA is testing their new equipment. All the results that I presented today are available in our deliverables. So far, we published 5 deliverables, 3 for Web Package 2. So the definition of use cases and KPI, the definition of scenarios for software simulations, the definition of scenarios for hardware demonstration and proof of concepts. One for Work Package 3 about the channel measurements, and one which is the latest about Work Package 4, where we reported some intermediate findings on physical layer enhancements for terahertz links. And they are all available in our website at this link over here. My last slide is about standardization and dissemination activities. As TeraMeta, we are actively collaborating to the HCI-SG terahertz. So 5 of the members of our consortium are also founding members of the ISG. So for example, we have Professor Thomas Körner from TU Braunschweig, who is our technical manager and is also the chair of the group. So far, we submitted some joint contributions, specifically on use case definitions and also on terahertz channel measurements. Then we are also contributing to the cost interaction by submitting joint temporary documents on channel measurements and modeling. And we also organized some dissemination activities together with other SNS projects such as 6G Shine and TeraMeta. For example, last November, we organized a special session at IEEE CSCN, and we will have a workshop this February in Bologna, and we also have a joint industrial session that was accepted at the ICC 2024. This is all from my side. Thank you for your attention.